Good morning. These are notes 12-2 for BC Calculus. Let's take a look at these notes for today and see how well we can do with these. So let's start out here with a set of inverse functions. Do a little bit of algebra review. So I already have my notes already filled out for you, so this is going to be a little bit different. Hopefully you guys can follow along as I reveal these. I do apologize for not having blanks to fill out with you, so I'll just explain what I have as we go through these. Okay? So let's take a look at our first set of problems. And again, we're looking at and doing a little bit of algebra review about inverse functions. So first of all, we're given this equation, y equals x cubed minus 1. And to do the inverse, we just switch our x and y's around. And we have x equals y cubed minus 1. The original function, this guy right here, is this snake that's been shifted down 1. And then when we do the inverse, it's just the same as reflecting that across the line y equals x. And this would be the graph of that inverse function. Let's practice another one. Over here, you'll see that we are given this equation, x equals y squared plus 2y plus 1. If I switch these guys around, I'll have y equals x squared plus 2x plus 2. That does factor to x plus 1. That's a little bit easier for me to see and graph. And of course, this is just going to be a parabola that has shifted to the left 1, and that's shown over here with this parabola. If I reflect that across the line y equals x, I'll have this parabola. Okay. Also, just a reminder, I'll save that for a little bit later. All right, let's take a look at our first problem here. I've already graphed this out again for you guys, but it is set up with two equations, and both of these are solved for x. Now, the easier one for me to graph is this guy. All I did was just add 2 to both sides, and I can see that this is just the line y equals x plus 2, slope of 1, y-intercept of 2, and we have this line right here. Okay. And then this one is a inverse of this parabola here. If I just switch my x's and y's, I know I'll have a parabola that was shifted up 4 and then is going down. Okay. So I'm going to reflect that across the line y equals x, and this up 4 would be a right 4. And then rather than going to the right, this negative changes it and causes it to go in this direction. Okay, so now we need to calculate the area between these two curves. And as you recall from yesterday, we look at the top and then subtract the bottom, top minus bottom. And in this region over here, you can clearly see that the line is above the parabola and we have a top minus bottom, except it could be a little bit confusing here because in this region, the parabola is also above the line. We just want this region here, so which one is which? And then we have another dilemma over here. Once we get to the positive x's, you'll see that for the region we're looking at, the top and the bottom is just the parabola itself. It's the top and it is the bottom, which means we can't solve this by doing a top minus bottom. But if you think about this, why not go ahead and cut it in this direction? Rather than making a bunch of rectangles that were a top minus bottom and adding all those up to get the area. Let's cut our rectangles this way. In other words, rather than a dx, let's do a dy. Add up all of these rectangles. As a result, we need to look at this as not a top minus bottom, but a right minus left. Let's take this right function and subtract the left function. That'll give me the length of this rectangle. Go to the next one. Right function minus left function, that rectangle. Right, left, right, left, right, left. And as a matter of fact, I need to take this from down here at the bottom, my bottom y value, and work my way up for each one of these. So when we look at this and we do what we would call a horizontal cut, this is the general equation that we're going to need to use. Okay. So in this case, that's going to give us the right function, which is the parabola. This one is the right function, minus the left function, which is the linear function, the y minus 2, with respect to y. Also, we need to take these limits, and these limits need to be y values, not x values. So we're going from y equals -3 to here, y equals 2. Also want to take a look at this by going ahead, and I put a little sketch over here of our inverse function. In other words, I just took and switched my x's and y's around, and when I did that, I graphed this one as the parabola that started at the vertex on the y-axis at 4 and opened down. And switching these around, I got the equation y equals x minus 2. So the y-intercept is here at -2 and it has a slope of 1. Okay. They intersect each other at -3, -5, and at 2, 0. Now I'm going to do the area of this by doing the vertical cuts that we did yesterday. The vertical cuts are going to have a top function minus a bottom function. Top function is the parabola. The bottom function is the line. Sorry about the noise there. Hopefully you can hear me okay. And let's take a look at this one. The inverse function is going to have the top being our parabola and the bottom being our line. And we're going to integrate this from x equals -3 to x equals 2. And the end result is the exact same as if we were to graph the inverse functions. Okay. So I'll go over this again with each one of these little inverse facts. And you can kind of see how each one come out here. So our first inverse fact is if we've got the ordered pair x, y on the original function, then y equals x will lie on our inverse function. As you recall, you did that way back in Algebra 1 when you just took your x, y t-chart and then switched the values around and made it a y, x one. And you could go ahead and graph each one of these the same way. Okay. I do want to point out to you to remember when you have lines, these two guys here that are inverses of each other, their slopes are going to be inverse slopes. Okay. So a slope of 1/2, the inverse would have a slope of 2. Okay, a 1 and a 1, that's pretty easy. In this case, both of these had a slope of 1 since 1 is the inverse of 1. Let's take a look at our next one. And that is the idea that when I graph these, as I showed on the very beginning, that the inverse functions can be done simply by reflecting the original function across the line y equals x. Just a quick little reflection. Another way of getting those is also by doing a flip and then rotating it. Okay. So I can flip my paper over, for example, this one. If I turn my paper over and then I rotate the top 90 degrees to the right, you'll see that this parabola and this line match that sketch that I did right here. I can achieve this graph by flipping my paper over and turning the top 90 degrees. Okay. Next, when you inverse a graph of two functions, the enclosed area, with an enclosed area, the area between the two curves remains exactly the same. Both of these areas up here in this example had the exact same areas. And then lastly, when you inverse a function, the right and the top are going to interchange, and the bottom and the left are going to interchange with each other. Okay? So let's do some examples of each one of these and see where we go. Okay? So our first example here is graphed out for us. And what you'll see is we've got this line that is the y equals 2x, and we've got this parabola y equals x squared minus 4 that are graphed for us. And it's pretty clear that we've got a top function, the line, and the bottom function are parabola. Intersection of this one, we can find that by, and that's shown right down here. I went ahead and set these two equal to each other. 2x equals x squared minus 4x. Subtract the 2x from both sides, factor out the x, and you can see we're going to have to integrate this from 0 to 6. Okay? So this one, when we looked at the sketch, it was pretty clear that this was going to be solved best by doing a vertical cut. In other words, our top minus bottom, and our boundaries are from the left intersection's x value to the right intersection's x value. So from left to right. And of course, like we mentioned yesterday, play it safe and let's do an absolute value. Okay. Let's take a look at our next example. In our next example, you'll see that they have graphed for us two sets of curve. One is somewhat parabolic, but of course it's a y to the 4th power, so it's a little bit flatter there than a straight up parabola. And our other one is somewhat of a snake shape to it. Okay. First of all, when I look at this and I start thinking like we thought yesterday, top minus bottom, you can see the dilemma appears here in the curve because the curve is both top and bottom. And then we run in the case where one curve is above, the other one's below. Just a mess if we try and cut this top minus bottom. Okay. So what do we need to do here? We surely need to look at this as a horizontal cut, a right minus left. And they have also solved both of these for x, and that's going to make it a little bit simpler and probably even trying to tell us for sure what to do on this one. So you can see here that the right function is the 1 minus y to the 4th. The left function throughout this whole region is the y cubed minus y. Okay. Notice again, these are always going to be solved for y. And then we need to use these two boundaries. First one is clear that it intersects at y equals -1. And then we're going to go to y equals 2. Okay, so our general equation, when we run into problems that are going to be better solved with horizontal cuts, is always a right minus left. This is a dy, and we're going to put as our boundaries from the bottom to the top, bottom to top. Make sure that these are y values, not x values. Okay. So on a multiple choice, I guarantee you one of the solutions that they're going to suggest will be with the x equals and for these as if it's going from left to right. Or okay. So now all we have to do is a few examples here, and in each one of these examples, there may be a case for a right minus left. There might be a case for a top minus bottom. Okay? And to do that, what we're going to want to do is go ahead and look at our graphs. Okay? So again, I've got this all kind of worked out for you, but I'll walk you through this. So first of all, you can see that our first equation, y equals x squared, is a simple parabola. And our second equation is also a parabola that is going down. And if I factor out the x, I can find my zeros rather quickly. A 0 at the origin, x equals 0, and the other 0 at x equals 2. So I can go ahead and graph this parabola. And it's pretty straightforward that this is indeed going to be a top, the upside down parabola, minus bottom, the upright parabola. Okay. Now, before I go on, I know some of you are watching this video and hopefully writing some things down. It is very important that you put this sketch down. As I grade your homework, this is going to be part of what I need to see. I want to see a sketch on every single one of these, just so that you know for sure whether you're going to have a top minus bottom, left minus right, and you can know where your boundaries are going to be. Okay, so we got our sketch out of the way. It's pretty clear that we've got a top function, the upside down parabola, minus a bottom function. And I think we know for sure that one of the intersections is at 0. The other one sure looks like 1. So to be safe, let's go ahead and set these two equal to each other and solve those. So subtract the 2x from both sides, add the x squared to both sides. We've got 2x squared minus 2x. Factor out the 2x. And you can see that indeed we have a 0 at x equals 0 and at x equals 1. So we're going to integrate this from 0 to 1. If this were a non-calculator, we could distribute this negative, combine the like terms, do our antiderivatives, and we would get 1/3. If it were a calculator portion, we can just put that right in our calculator. Reminder again, just to play it safe, we'll put our absolute values around these. Let's take a look at our next example. In this one, we have two curves that we're going to do the area bounded by both of those. Both of these are written as it were like an inverse function. And this one's pretty easy to just manipulate so we can graph. It's just going to be the graph y equals x minus 1. This one, we know that it's going to be a parabolic shape, but of course it's going to be either opening to the right or opening to the left. Since this is positive, it should open to the right. And since this is negative, we should start at -3 on the x-axis. So indeed, I've graphed those for you. You can see that the parabola, this is at x equals -3, and it's going to open to the right like this. And our second equation is the line with the y-intercept at -1 and a slope of 1, and I've drawn it like this. Okay. So this immediately presents us hopefully you can see as top minus bottom in this region might be able to work itself out. We have a little bit of dilemma as to whether we're using the parabola that's above or below that. But then as soon as we get over here, things get really messy. So no reason to try and chop this up and do vertical cuts on this. It's a straightforward horizontal cut. And so you can see the right function is the linear function. The left function is this parabolic function. So we have a right minus left with our absolute value and with respect to y. We also need to find our boundaries. We do that by setting these two equal to each other. Okay, and this very well could be a non-calculator problem. So make sure that you're able to do this algebra step. First thing I did was went ahead and multiplied both sides by 2 to get rid of that 1/2. Then moved everything to the left-hand side. Y squared minus 2y minus 8 does factor. That factors to y minus 4, y plus 2, which gives us the two intersection points at y equals -2, our bottom boundary, to y equals +4, the upper. Put that in your calculator and you'll get 18. This one, again, could be a non-calculator. You could see distributing the negative, combining like terms, antiderivative, evaluate from -2 to 4, you would also get 18. Okay. Let's take a look at our next example. Okay, both of these you can see are, oh no, one of them solved for y, one of them solved for x. The solve for y one is pretty straightforward. It's just going to be this snake, regular old snake, nothing changing about it, y equals x cubed. And this one is another parabola that does open to the right and starts at x equals -2. And that's shown by this guy. With a quick look at this, vertical cuts are going to be a dilemma. So this does present us as a right minus left with horizontal cuts. The right function is going to be our snake. But remember, when I substitute this in, if I'm doing horizontal cuts, I can't have any x's. So I need to solve this one for y. I'm not doing the inverse of it. I'm solving this equation for y, or solving it for x. It's already solved for y by taking the cube root of both sides. And that'll give us y to the 1/3 power. That's our, in this case, the right function. And then our left function is already solved for x, so it's going to be a y squared minus 2, and that's our left. It's always to the left over here. We'll do the same thing to find, or we do need to do the same steps we did before to find the boundaries. And depending on what skills you have with your calculator and how you use your calculator, one way would be just put the first equation here, x equals y, or the cube root of y, and put that in your y1, the y squared minus 2 into y2, graph it and find the intersections. Okay. Or you could manipulate the equation by subtracting from both sides and put that in your calculator and find the zeros. Regardless of your method, you'll find that we're going from y equals -1 here to y equals 1.7930. And yes, I put the 0 there because they're looking for 4 decimals in the intermediate step. And this one, of course, is the bottom. This one is the top, and that's shown in our integration. Put that in our calculator, add a little absolute value. Hopefully by now you're able to find where that absolute value function is on your calculator to use that. And our end result would be 4.214 for the final answer. And let's take a look at one final example here. This one has a simple little parabola associated with it. It's just this guy right here. And then a line that has a y-intercept at -2 and a slope of 1 going like that. Oh, and we're also cutting this off at the x-axis. So this one's asking us to find this region here. Some of you might recognize that and say, hey, wait a second, we already did that one. We did that one yesterday, and we did. Matter of fact, we found 3 or 4 different ways to solve this one yesterday. But hopefully now what you can see is, wait a second here, all that work I did yesterday, what if I instead made horizontal cuts on this one? What would I get out of that? Would I get the same answer? Well, of course I should. And I might get it a lot easier because you can see that this line here is always to the right. So in other words, the y equals x minus 2, if I solve that and use x equals y plus 2, that's going to be my right function on this one, y plus 2. And then the left function is just going to be this guy right here. That left function, y equals the square root of x, would be x equals y squared minus y squared. That's my left minus my right with respect to y. And if I set these two guys equal to each other, y squared equals y plus 2, y squared minus y minus 2 would equal 0, or y minus 2 and a y plus, sure why I added that in there, plus 1 would equal 0. That gives us the intersection at y equals 2 and y equals -1. This one is not necessary because we know we're going here from y equals 0, and we're going to integrate that to y equals 2, from 0 to 2. And guess what? We have solved the same problem we did yesterday in a lot easier fashion, rather than have to split this up and do, we did some with a little bit of addition, some with a little bit of subtraction, some with a couple different subtractions in them. Okay? So that's kind of the moral of the story for today, is make sure, like I mentioned to you, every single problem, go ahead, make the sketch. That's going to be part of the credit on your homework. That's going to be part of the credit on a quiz. That's going to be part of the credit on the test. Make your sketch, determine, should I use a top minus bottom or a right minus left? Make sure that you're only having x's in the top minus bottom, only y's on the right minus left. Also, make sure you read it carefully, because some of them, sometimes they say, well, just the area in the first quadrant or the area in the second quadrant. So read the question carefully, make sure you understand when the y-axis is a bound or the x-axis is a bound, and there you go. So hopefully you did well with this one. I think it's a pretty straightforward lesson for you. I wish you well, and I will see you hopefully tomorrow.